Point Deform. A lot of people use it for every kind of deformation, and that really breaks my heart because there's lots of better ways to deform things depending what you're doing. So in this video I'll go through my favorite methods and why you might want to use them. First, whenever you're deforming something, you got to think about the domain. Some methods like Point Deform only care about the points making up the object, whereas others think about the surface in between the points, or the volume inside the surface. As you'll see, this makes a massive difference and it's really important to think about. Let's start with the first type, which is Point Deform. You probably know how it works already. It takes some input geometry, in this case a single point, and 2 bits of geometry to distort the point with. First it takes the rest geometry and it adds these little arrows to each of the points, and these arrows represent transforms, so each point gets its own transform. The transformations actually look like this. It tries to align them roughly to the edge, but for simplicity I'm just going to draw them like this. Then it takes whatever you're trying to parent and attaches it to the nearest transform. In this case I've got the maximum point set to 1, so it's only using the transform of the nearest point. But if I set it to a higher number, it does basically a weighted average of all the transforms. Changing the radius changes the size of the sphere it searches within. If the sphere is too small, it might not hit any transforms. To fix that, you can increase the minimum points, so even if it's outside the sphere, it picks at least a few. So once it's picked a few transforms, it'll distort the geometry. And if I move the point around, it'll change the transforms that it picks. Now keep in mind it's not really aware of the faces in between the points, it's only based on the points themselves, and this causes problems in some cases. For example, here I've got some other geometry, and I want to deform it something like this, so twisting around. If I use Point Deform, you get this really weird result where everything twists into itself. That is because I don't have enough points. You can see this if you visualize it. It's only using the coordinates of these points, so it ends up parenting across to the wrong transform, and that causes the kind of distortion behavior you see. All of these points end up twisting with the wrong transformation. This is a very common problem with Point Deform. Now I know what you're thinking, and that's you can use the piece attribute to avoid this problem. And that's true. I mean, in this case I have a copy num that's unique to each of them, and so I can use that with Point Deform to separate out the pieces, and now they're parenting to the right transforms again. But this doesn't always work in all cases. Here's another example. I've got a patch and I'm scattering some points along the surface, and I want those points to scale outwards and then expand like this. Watch what happens if I use Point Deform. They split in kind of a Voronoi-like way, and you'll notice the center of each of the patches aligns perfectly with the points of the grid. Now you might say you can mess with the settings to get a better result, like increasing the radius or the number of points, but you can see this really doesn't work very well. The points aren't really sticking with the surface at all, they're sliding around and giving this weird result. So what could you do to fix this? Well, what you need is a different type of coordinate system. One coordinate system you might think of using is a UV map, because it takes a 3D position and maps it onto a 2D position. The problem with the UV map is the faces might overlap, and then the mapping's not unique. That means points across the geometry map to the same location in the UV map. So what can you do to get a better mapping? Well, Houdini uses something called primitive UVs. Don't get this confused with regular UVs, it's a different coordinate system and it doesn't need a UV map. It's made up of 2 bits of information. The first bit is the primitive number, which I'm drawing here. You can see the numbers by enabling this visualizer, and importantly, each primitive has a unique number. So that's the first bit of the coordinate system. The next is a UV coordinate, and this works just like a UV map. You can see it's actually overlapping completely in the UV viewport. But these two things combined together ensure the mapping is unique, because even though these UVs are overlapping, the primitive numbers are not. Now there's many nodes that support primitive UVs. One of those is scatter, with the primitive number and the primitive UV. So you can scatter points on the surface, get their primitive number and UV, and then use attribute interpolate to look up the corresponding location. And you can see this fixes the problem I had before, because now it's aware there's faces in between. You can also do it using a ray node. So a ray node also gives you the primitive number and primitive UV, and that lets you do another coordinate system. Or if you like Vex, you can do it with XYZ dist and primuv, which does exactly the same thing. But there's one problem with this approach. What if you have a surface and then points slightly above the surface? If you use primuv, it's just going to snap them back down because it doesn't have any awareness that there's an offset. So how would you account for the offset? Well, that's where this node called Surface Deform comes in. Surface Deform is based on the primitive UVs. It samples the nearest coordinate, and then it adds the offset in terms of this little axis. That means when you stretch out the plane, it stays anchored to each of the faces. And you can even bend the plane and it stays anchored within the same distance to the surface. Now, one thing you have to be careful about is the subdivision option. It gives a nice smooth result, but it might also cause clipping if you're doing it for something like a cloth sim. So make sure to turn it off by default. Surface Deform is very good for cloth. For example, imagine this cylinder is an arm bending, and I've got this cloth that I want to put on top of the arm. Point Deform gives me this really nasty result, and I can try cleaning it up with the radius slider, but it results in these really weird patterns and these clipping artifacts. Compare that to Surface Deform. Now I'm getting a much cleaner result without any clipping of any kind. Now keep in mind, if you turn on subdivision, it will clip, because now it's treating it as a smooth surface. But otherwise it gives a very good result, and you can even blur it to get more smoothness. Now another node I want to shout out is the Wrap node from Momme. It's a very good alternative to Surface Deform, and it gives much cleaner results. So there's a link in the description where you can download this node. Now what if I wanted to form something inside an object, like these points? I've got a cube that I'm scaling upwards like this, and if I use Point Deform, it rips them apart down the middle. If I change the maximum points or the radius, you end up with a slightly better result, but it starts to bend. Surface Deform isn't much better. It gives an even more janky result. So what can you do in this case? Well, one option is using tetrahedrons. Tetrahedrons are a volume-based representation of geometry. What that means is it turns it from a 2D surface into these 3D triangles with volume inside them. These triangles have UVs that are actually 3D, so whenever you look up a coordinate, it actually maps to a 3D coordinate instead of a 2D coordinate. You can get the coordinate using a ray node, and then if I distort the tetrahedrons, for example stretching them upwards, the points are now getting stretched correctly because they're using the true 3D coordinate. But it's not always possible to use tetrahedrons because the triangulation changes as the geometry changes. So what could you do? Well, another approach is positive mean value coordinates. The idea is each point inside the object shoots out rays in a sphere. Some of the rays get stuck to the wall, and that means when you pull the wall, it pulls the point in that direction. If you repeat this process for all the points, they all get very sticky, and as you pull the wall around, you get this crazy spiderweb look. This lets you deform respecting occlusion. For example, this point in the corner doesn't see the wall, so it doesn't move at all, whereas the ones over here do because they're able to see the wall. The same concept works in 3D. Each of the points shoot out rays in a sphere, and then each of them gets stretched as the cube gets stretched. Now I've made a node you can download in the description called Volumetric Deform based on this method. It lets you stretch out points with respect to the volume. The number of samples controls the number of lines that are being shot out, so the more samples you have, the better quality the deform will be. And I want to thank Sibarrick for coming up with this method. I just translated what he did into Vex to make it a bit faster. Now all of these methods, point, surface and volume, assume the object's bending around, but if it's a rigid object, things are much easier. For example, here I've got this animation of a plane, and this animation consists of two packed bits of geometry, and I want to parent this pig so he's sitting on top of the plane. Now the advantage with packed geometry is it usually comes with a transform, so you don't need to do any of this other crap to recalculate it. You can check that by going to the spreadsheet and going to packed full transform. This should have a matrix that should change over time. Another way to check is using a packed properties node. If you drop this down and set the visibility to bounding box, you should see a moving box representing the transform. This means I should be able to copy the transform from that rectangle directly onto the pig. First I want to position the pig in the right location. I'm going to do that by taking this plane and using an unpack node. The unpack node has an option called apply transform. If you untick it, it deletes that transform that you saw in the spreadsheet, and this is the rest position of the plane. If you play through, it shouldn't be moving. Otherwise you might need to unpack multiple times. Now I can position the pig where I want him to be. For example, I'm moving him right up to the front. Now I want to copy the transform from the body of the plane. To do that, I first want to isolate the body of the plane using a blast node. If I plug in the blast node and select just the body and delete non-selected, this plane is basically a single point with a transform on it. That means I can use this node called transform pieces. The template point is going to be the plane. Geometry is going to be the pig. And now the pig sits exactly where I want him to be. I'll merge him onto the plane, and then he can go off on his merry adventure. Goodbye, my love. or I can attach him to the propeller so he never leaves me again. Now Jeremy is watching this all unfold, but he's not thinking about the pig, he's wanting to move somewhere else. Now I have no way of knowing what transform I need because it's inside a black box. He's not packed geometry, so I can't use anything with packed transforms. But what I can use is extract transform. This node estimates the transform from one location to another. It gives you a single point with transform attributes on it that you can use with transform pieces. So if I plug in transform pieces, it takes him to the position of this pink guy, even though I have no idea what transform it actually took. Now extract transform assumes the topology is the same, meaning the point count is the same and the point order is the same. That means if you remesh, it's not going to work, it's going to give you an error. But why is it useful? Well, let's say we have the same example as before. We have the pig and we have the plane. Now I want the pig to sit on top of the plane like before, but in this case it's not packed. So what can I do? Well, first I'll start by blasting away all the faces I don't want to use. So I'll just keep the top face of the plane. Now this face is moving over time, which is no good. So I'm going to need to freeze it using a time shift node. Now the face is frozen and I want to move it back to the center to make it easier to work with. So now it's in the center, matching where my pig is. And just like before, I can position the pig where I want him to be. Now what I can do is use an extract transform node. For the reference geometry, I select the frozen version, and the target geometry, I select the animated version. That gives me the transform from the resting version to the animated version. So then I can plug that into transform pieces, plug in the pig, plug in the transform, and now, just like before, he's sitting on top of the plane. And of course, you can move him around to all the different faces, including the propeller. Now the final thing is volumes, or VDBs. Even though volumes contain a bunch of voxels, you can see with visualized tree, you can't easily fiddle around with their locations without rebuilding the entire volume. That's what volume deform does. Volume deform basically takes a grid of points, then you can stretch out or distort that grid, and it rebuilds the entire volume to respect those changes. Now volume deform gives you great quality results, but if you're feeling hacky, you can actually use volume rasterize attributes. Now this gives very dotty results because what I'm doing is actually taking the volume, taking the points inside the volume, adding values to them, and then deforming those points directly. Point deform, again, probably not the best choice, but it gives a good enough result that you might get away with a simple translation or a shear, for example. So thanks for watching this video. I've included this file in the description as well. Of course, I haven't covered the other 3 million deforming nodes in Houdini, but this at least covers the general use cases that I run into the most. So check out this file if you want, and I'll see you later.